Like I said before, this definition of vectors and vector space allow us to view more things which are not necessarily vectors in the usual sense as a vector. So let's just look at the example here. So, for the example of 3.1, I'd like to show that the set of all complex numbers is actually a vector space. So, to check that something is a vector space, all I have to do is that I just need to check it against the 12 definitions, the 12 properties that I have. As long as the set of all complex numbers has all these 12 properties, then it's going to be a vector space. So let's look at them one by one. For the first one, if I add two complex, so my u and v now here, it's not vector in your usual sense, it's going to be your complex number. So let's just say if I have two vectors, c1 is x1 plus y1i, and then c2 is x2 plus y2i. If I add these two complex numbers, I'm going to get c1 plus c2, and that's going to be voila, x1 plus x2 plus y1 plus y2i. This is also a complex number, so it still remains a complex number, so it satisfies my first properties. My 0 plus 0i, this is 0, this is also a complex number, so it belongs to my set. If I multiply a complex number, so my v, this is a complex number. If I multiply a complex number with a scalar, and by scalar, it's going to be a real number. If I multiply a real number by a complex number, the product is going to be, well, also a complex number, so it remains in my set. Remember again, my v is, here is the set of a complex number. Negative 1 times v, or the negative v, a negative of a complex number is also a complex number, so this one's checked. And then the remaining 8 is going to be kind of obvious. If I add the two complex number u plus v, it's going to be the same as v plus u. And then the associative property, we also have that. If I add a vector, by which I mean a complex number, by 0, then I get the same thing. If I add a complex number by its negative, then I'm going to get a 0, this one I have. If I multiply a real number a to the sum of two complex numbers u and v, that's the same as the sum au and av. So this property, the complex number also already have. This one is okay, this one is okay. And then if I multiply 1 to any complex number, I get the same thing. So complex number has this property. So that means the set of all complex numbers, it actually has all these 12 properties. So it's automatically a vector space. So like I said before, the definition of vector space that we have will allow us to view a lot more objects as a vector. So we can study these guys as also a vector space. Now let's look at the next example. I'd like to verify that the set of all quadratic polynomials. So now I'm looking at all the quadratic polynomial, and quadratic polynomials are polynomials that have degree at most 2. So I'm going to have a times x squared plus b times x plus c, where my a, b, and c are a real number. So I need to verify that this guy is also a vector space. So once again, as usual, I'm just going to check the 12 properties. As long as the set of all quadratic polynomials has these 12 properties, then I'm okay. Then that is going to be a vector space. First thing first, is the addition of two quadratic polynomial also a quadratic polynomial? So if I have two quadratic polynomials, let's say a1x squared plus b1x plus c1, and then a2x squared plus b2x plus c2. If you add these two guys, you're gonna get, well, a1 plus a2x squared plus b1 plus b2x plus c1 plus c2. This one is also a quadratic polynomial, so that means if I add any two quadratic polynomials, I'm gonna get a quadratic polynomial. So I have this property. So quadratic polynomials is closed under addition. I also have a 0. So if I have 0x squared plus 0x plus 0, that's going to be a 0. So my quadratic polynomials has the 0 vector. If I multiply a number to a quadratic polynomial, it is also going to be a quadratic polynomial. So I have the third properties. The negation of any quadratic polynomial is going to be a quadratic polynomial. The negation of, let's say, the negation of this guy is just going to be negative a1x squared minus b1, minus b1x minus c1. This is also a quadratic polynomial, so no problem here. And the remaining 8, that should be easy to see. If I add two polynomials, it doesn't matter which order I add them. I can add v plus u. So my v and my u here, my v and my u here are actually polynomials. So they are not actually vectors in the usual sense. If I add u plus v, that's the same as v plus u. So that's okay. If I add u and v first and then add w, that's the same as adding v and w first and then add that to u. If I add the zero polynomial to any other polynomial, I get the same thing. If I add any polynomial here by its negation, this guy, then I'm gonna get the zero vector. So I have this one. I also have the distributive property. A times u plus v is the same as au plus av, and then a plus b times v is ab plus bv. So I have this one. A times bv is ab times v. So I already have this one. And then if I multiply 1 to any polynomial, if I multiply 1 to this guy, I'm gonna get the same thing. So I already have this properties. So that means my set of quadratic polynomial has these 12 properties, and that's why it is automatically a vector space. Now, I'd like to point out one thing. I said earlier that we do not require that two vectors be able to be multiplied, which actually is helpful in this case because notice how if I actually multiply two vectors, if I multiply two quadratic polynomials, a1x squared plus b1x plus c1, if I multiply this by a2x squared plus b2x plus c2, if I multiply this two guys, I'm gonna get something which is not a quadratic polynomial. I'm gonna have x to the fourth a1, a2. If I multiply these two guys, I'm going to have something in the fourth and in the cube power. Something like this. Which is no longer a vector, which is no longer a quadratic polynomial, but this is okay. And that's because my definition doesn't actually ask me to be able to multiply two vectors. So if you want to check whether something is a vector space, you only have to check that you can add two vectors and it remains in your original set, and you can multiply your vector by a scalar, by a real number, and it remains in your original set.